Hi, and welcome to week 5, the process of science. Our goals for this week is to develop an understanding of each of the basic and integrated processes of science and understand how different processes relate to one another. We also want to articulate how some processes change across grade bands and understand the relationship between these science processes and the science and engineering practices in a framework for K-12 education. This week, your reading assignment is to read Chapter 3, The Process of Science. There's a lot of activities in there, and you should definitely scan over all of the activities. You really only need to read in depth the activities that you're requested to in the activity look at, and it always tells you how to select which one or which ones to look at. There are a bunch of videos to watch. There are 5 short videos on YouTube in addition to this video that kind of give you some either kind of an updated version or a classroom-based version, or maybe just another perspective on some of the processes or practices that we're talking about this week. In the book activities, you're going to need to look more closely at activities for observation, classification, identifying and controlling variables, and then you'll do some compare and contrast with the predictions and forming hypotheses ones. And look across grade bands for experimenting and constructing models. And then there's an activity that'll ask you to look at from a program called CIRC that uses some old faithful data, and you don't have to actually do the activity. I just want you to look at the activity in the context of analyzing data. So like I said, one of the goals for this week is to really think about how the practices from the framework for K-12 education integrate or merge or overlap or relate to the processes that we're talking about this week. So I just want to kind of remind you that those practices were asking questions and defining problems, developing and using models, which is one of the processes that we're talking about this week, planning and carrying out investigations, which is one of the processes we're talking about this week, analyzing and interpreting data, again, a process that we're talking about this week, using mathematics and computational thinking, constructing explanations and designing solutions, which looks a little bit like communicating, but is a little bit more complex, engaging in argument from evidence, and then obtaining, evaluating, and communicating information, which has some relationship to some of these processes but isn't exactly the same. And again, we talked about this streamlining of the practices, that we can put them into this kind of these packages of practices we use to gather evidence, practices we use to construct explanations, and practices we use to communicate reasoning. We could do something similar with the processes that we'll talk about this week. And as we think about those similarities, what we're really thinking about is that some of these processes are things we use to gather evidence or things we use to construct explanations, and they're just being packaged a little bit differently than the practices for K-12 science education. And I've chosen to use this section of the book despite that kind of language barrier, because I think there's a lot of really important stuff in here for elementary science teachers to think about in terms of the things they might do in their classroom. And that will be my focus as we talk about these processes, is what do you need to make sure you're providing students practice with, providing them opportunities to do. So the basic processes of science, we'll talk about those first, are observing, classifying, communicating, measuring, predicting, and inferring. And the great news about these basic processes of science is that these are also basic processes of life. You'll find that students, no matter what age, group, grade level, whatever, will have lots of prior experience with these processes. Your job in the context of science will be to expand their experiences to include some of the nuance that is specific to science. So the first one is observation. Observations are the foundation of science. No matter what we do in science, we're using observation as our starting point. To me, the single most important thing for elementary science teachers to understand is that students need opportunities to practice observing. They need to have practice with qualitative and quantitative observation. They need practice with formal lab environments and with less formal lab environments like the outdoors. In our state, a huge portion of working scientists actually formally practice in science outdoors. Many of these individuals will work with schools, or they participate in programs that run through museums, extended universities, informal science providers, or even government agencies. So it's really important to provide students with those opportunities to think about all the different environments where science happens. And so capitalizing on those informal providers can be a great way to do that. Another important piece is providing opportunities for students to discuss their observations with each other. This allows them to see the variety of observations that can be made and helps them be more aware of the things they don't naturally notice. I know that as you think about the experiences, and as you select the activity from the book and practice your observation skills, you'll find that there's kind of a really big focus on observing the things you don't normally see, and having those group discussions can really help kids to be aware of things that weren't their first observation. The next skill is classifying. Students will have prior experience with putting things into groups. The key in science, though, is to classify at multiple levels. You know, we all kind of have this tendency to want to group things. And like the shapes at the top, that would be an example of classification they might have done in math. They can group things by the same shapes. They can group things by the same colors. There's a lot of different ways that grouping could be done. In science, what we end up doing really, though, is grouping at multiple levels. And so we could classify by shape and then by color and have all of the triangles kind of separated out, but then within that also separate out all the green triangles. And you can kind of see that illustration here with this. We could classify just by animals. We could definitely take this another level. And we want to be really careful as we think about these classifications, because we want to make sure that they're meaningful, and sometimes you need that second layer to make it meaningful. And here's another example. This is of a two-layered classification. Matter, is it variable, yes or no? If it's a pure substance, it could be an element, it could be a compound. If it is variable, it's a mixture, but it could be a heterogeneous or a homogeneous mixture, and each of those has some different characteristics. So I want you to select an activity in the book and actually practice your classification skills and kind of take yourself back to that experience of being young and thinking about categorizing different things. I know even in high school, we often, as a beginning of the year activity in our science classes, would have students all take their shoes off and practice classifying them, trying to come up with those categories that could make sense of all the different shoes that were in the classroom that day. This is a really important skill. The next science process is communicating, and it's important that students have opportunities to communicate with their peers. I like this illustration because I feel like this is really what happens sometimes. We put something out there and it gets kind of all jumbled up before it's received by another person. So the three types of practice I want you to think about focusing on is, one, provide them an opportunity to communicate with a more knowledgeable individual, someone like you, a volunteer, an older student. These people are able to provide a scaffold to good communication by asking good questions and guiding them to those meaningful expressions that a peer, a true peer, an equal, might not be able to actually ask the right questions to help them to get that good communication down. We also want to think about using graphic organizers or other assisting tools to get that effective communication down. A lot of times graphic organizers can help students to figure out where the missing pieces are without having to hear from someone else that it wasn't understood. And then also hearing the communication of others. So having the opportunity to hear somebody else's explanation and identify why it was hard for them to understand can help them to better communicate with their peers. Communication is so vital in science for validity, for reproducibility, for a shared understandings of concepts and content. We can think about what we just talked about in classification. If I can't communicate the groups I'm classifying into very well, you're not going to be able to reproduce my classification scheme, and you might put animals in different groups. If instead of saying fish and mammals, I said, creatures with fur and creatures that swim, it would be very unclear where to put whales in some of our non-traditional or unique mammal examples. Measuring is a basic skill. It's a great place for interdisciplinary work with mathematics. Those of you familiar with the Common Core standards for elementary and mathematics know that measurement is a section in there. Knowing how to make and manipulate measurements is really vital to science, and especially when we're making those quantitative observations. And so this is a great opportunity to fit science in to those math and reading time periods that have to be done based on district standards. It's really important to provide students practice with all different types of measurement. The experience of measuring time is really different from the experience of measuring length, and especially with young children, it's good to provide at least a reference point, even though we want to use metric units, providing them that reference point of conventional units as we give them those experiences. So for example, students might really not have any idea what it means that something's a meter long, but they might know that they're 3 feet tall. And so giving students those experiences with both types of units as they learn to convert and kind of interpret between the two is really important. Another really helpful thing is non-standard units. It's a great way to prepare students for the variety of experiences they're going to have down the road, both times where they need to use a non-standard unit because they don't have the best tool available to them, or times when they're working with unfamiliar units, especially as they move into the domains of science where they have measurements that they can't actually experience. So it's a lot easier to gain personal experience with what a foot is, what it feels like, and compare that to a meter and then begin to really understand what a meter is. But something like volts and amps, it's a lot less concrete. And so one of the great things about non-standard units and being able to think about different types of units is that when we get into those non-concrete units later, that can be really helpful. It's also good to give students experience with different levels of precision. There are times when it's okay to round to the nearest centimeter and times when it's not. And so helping students to see what precision is and why we have those different levels is really important. Predicting, this basic process here in predictions is something we do every day. And we'll talk more about some really specific types of predictions when we talk about hypotheses. But when it comes to these basic predictions, we want to give students practice with seeing patterns, thinking about what will happen as the pattern continues, and then making predictions about things based on those patterns. We also want to give them an opportunity to track their predictions, see if it came true, and explaining those predictions. So if I see a pattern and I make a prediction, being able to tell you why that pattern led me to that prediction is a really important part. There's also really great value in giving students opportunities to make predictions outside of the formal process of writing hypotheses that we'll talk about later. But one of the reasons that this is important is it provides a safe space for failure. A lot of students feel uncomfortable with hypotheses because they want to be right. They have this formal lab, they have this hypothesis they're supposed to write with this special format, and they don't want to go to all that trouble and have it be wrong. They also don't want to have to write about how it was wrong later. So taking the opportunity to make predictions, whether it's as a group or individually, explaining them, evaluating them, talking about it together, gives them a chance to experience that productive failure and be more comfortable with the idea that sometimes we need to just take a stab at it, see what happens, and be ready to explain what actually happened later and why our prediction went wrong. It's also really useful because it helps students to see that they pay attention in a different way when they've made a prediction than if they're just observing events unfolding without taking that step. So taking that pause to ask students what they think is going to happen, just like you might do in a story when you ask them to predict what will happen next in the story. Doing that with everyday events and with science events is really valuable even when we're not going to go to the next step of that formal hypothesis. The next process is inferring. Humans are naturals at inferring. We do it without realizing it a lot of the times. One of the greatest things you can teach your students is the ability to distinguish between an observation and an inference. Okay, so giving kids the opportunity to record their observations and record their inferences and to have a separate spot for an inference, it really helps them because they want to tell you their inference. I know that if you think about a child, whether it's anywhere in the elementary grades and even in high school, to be honest, writing down just exactly what you see and not being able to say, and I know that this means, or I think that this means, is really hard because you want to show what you know and what you understand. And so leaving that space for kids to write their inferences separately can be really helpful to them in keeping those observations clean. Ask students to practice explaining their inferential reasoning. So what observation are you building off of? What prior knowledge or previous experience are you drawing from? And then allow students to discuss their inferences and revise them. Sometimes another individual will reference a piece of prior knowledge or an observation that a student didn't think of, and they're able to think critically about which information was actually better for making an inference. So what inference should I make? That's a great opportunity for critical thinking. And this image is taken from the video that you'll watch that kind of talks about observations and inferences. It goes on to more detail about observations, but it does a great job of kind of asking you to think about which things about this bug is an observation and which things about this bug are an inference. The integrated processes of science are things that pull together kind of more pieces. They're not kind of at that basic level. And they are identifying and controlling variables, formulating and testing hypotheses, interpreting data, defining operationally, experimenting and constructing models. So identifying and controlling variables, our ability to conduct meaningful experiments is lost without an understanding of variables and how to control them. It's really important that you provide students with the opportunity to think about all the different variables affecting a situation. Even if you're doing a canned or a preset lab, ask them what things are being held constant or what could be changing that they need to watch for. This will really be essential later as they strive to understand errors in their own experimental designs. We also want to make sure that we provide students with an opportunity to identify independent and dependent variables. Now, the description of independent and dependent variables in my version of the text comes up later in experiments, but I feel like that's a really important part actually of just identifying variables separate from an experiment. They need to learn these words. And you know, for younger kids, those are hard, but they can still get behind the idea that changing one thing and observing something else is how we do experiments while we hold other things constant. And so kids can definitely use these terms to describe that thing that they're doing. So identifying those independent and dependent variables is really important. We also need to give opportunities for the students to think about how they can control the variables that need to be held constant. And so once they've listed all those controlled variables, to have them identify what can they do to hold that the same. Kids come up with the greatest examples for that. I love, especially in a lot of physical science labs where they're trying to manipulate or drag or pull or push or drop, and having kids try to think of ways to make sure they're always pulling at the same angle or always pulling at the same speed or always dropping it from the same height. All of these different things that they can think through and identify their own ways. It also is a really good way to help them be more observant of their surroundings and observant of having a positive experimental design. So the book has a bunch of activities for controlling variables, and this is one that I want you to select an activity and kind of think through what would the variables be. It's one thing to just hear me say, identify potential variables or identify the method for controlling them. It's another thing to really look at some examples of that and kind of practice with identifying them. The next thing is formulating and testing a hypothesis. And kids get a lot of practice writing hypotheses during their years in school. And my suggestions here are kind of ways to think about varying the process or look at it from some other angles. They're all designed to give students opportunities to build their skills with the process beyond just having the idea that it needs to be an if-then statement, which was pretty much the most common thing that my juniors in high schools came to me saying, a hypothesis has to be an if-then, and that's the long and the short of it. So kind of understanding with greater depth about what a hypothesis is. So the first suggestion I have is to let them follow a formula, and it doesn't always have to be an if-then, but to give them a structured sentence like a fill in the blank. With that kind of traditional structure of I have an independent variable, and as I modify that, this is what I should see in my dependent variable. Whatever version of that structure you want to give them, but actually to give them that structure. The next is to have them write their hypothesis in a group. This takes a little bit of pressure off the individuals. With this formal process, they can get kind of worried about being wrong. And if the group kind of comes to a group decision, it helps the individual to feel like if I was wrong together with these other people. There was something that we all kind of were thinking, or this was tricky in some way. Another great thing is to have students build background knowledge first and then write a hypothesis and think about how that's different. You can even have them write a hypothesis, then go read something, build some background knowledge, and then revise before they do their experiment. And this is really most like science in the real world, where we have an idea of what might happen, we kind of write that idea down, we go and read a bunch of stuff that other people did before we come back and actually invest in our own experiment. We also want to have students think about the opposite of their hypothesis. This really helps them to think about what they're going to see if it goes wrong. What would that data look like? What would that experiment look like? And this is a great way to help students to really think through how the independent variable is affecting the dependent variable and what the experiment is really getting at. So when they write their hypothesis, to say, if you're wrong, what would you see instead? What would the opposite be? In your book, I'm going to ask you to look at the activities for predictions and the activities for formulating and testing hypotheses, and really think about how these processes are similar and different in practice. What does it really mean to have that formality of the hypothesis forming and testing? For interpreting data, when we analyze data, that takes a really different shape at different grade bands. A symbolic bar graph is a sophisticated method of analysis in kindergarten. In 8th grade, not so much. So at all grade levels, students should have some opportunities to practice some things. So one is to think about how they're designing their data table and how that affects their interpretation of data later. You know, where you put your independent and dependent variable on your data table actually makes a difference. And so getting kids to practice that and to think about that design is a great first step in interpreting data. The next is to give students the opportunity to experiment with different types of graphs, see which one makes their interpretation make the most sense or easiest. And then the last and most important is asking them to explain and justify their interpretations. And having the right data table and the right graph is definitely really important to having good justification. But even young children can say why they think the data shows something. For this one, I'm not asking you to look at an activity in your book. I've actually given you a link to an activity for Old Faithful. There's a bunch of data on Old Faithful's eruptions, and this activity is one that can be used with students to think about how you could graph that and how different ways that you graph it would lead you to different conclusions. I don't want you to go through and do the activity itself. I just kind of want you to look at it and think about how how using data in that way is meaningful to students. The next one is defining operationally. And I love this quote from The Princess Bride. You keep using that word. I do not think it means what you think it means. We have that with kids a lot. They use these words and they really don't mean what they think it means. And sometimes that is because they just don't know the definition, and sometimes it's because you need an operational definition. So when I think of operational definitions, I remember this time in grad school when I was watching a video, and I wish I could get access to it to show it to you. It showed a group of students learning geometry through quilting. And the students had each made a geometric quilt block. I think it was out of paper, not fabric. And they were sitting during circle time sharing with the class, and they each had put their quilt blocks up on the board, and they had to explain what they were seeing in the blocks. And they would come upon things they didn't have a word for, and they'd create a word that made sense to them and put it on the board with the definition. It was fascinating to watch. The kids accurately described some pretty intense concepts like symmetry, parallel, congruent. I mean, these were like second grade kids, and they did that on their own by looking at this thing and saying, well, symmetry, and they had their own word, not symmetry. It was like, I don't remember what their words were, but symmetry is when you have these two things and they're the same as each other, and I could make a line, and on each side of the line it's like I'm using a mirror. I mean, those were the things that the kids were coming up with on their own. And so this idea of operational definitions and giving students the opportunity to say, when I'm using this word, this is what I mean. So it happens a lot in science. And I like the example in the book about floating, where it says, you know, what do we call the thing that goes underwater? It's completely under the water, but it doesn't drop all the way to the boat at bottom. That doesn't match my definition of floating. That doesn't match my definition of sinking. I either need a new word for that or I need to modify one of my two definitions. And so this process then of coming to this agreement about what we're going to mean by things. So we need to stop and do these, and that's part of communicating in science. So one of the really good things that you can do is helping students to identify the terms that require an operational definition. When they're looking through, what do you mean by light? You know, you're doing an experiment with a plant and you say that you're going to expose it to light. Well, what does that mean? Does that mean sunlight? Does that mean lamplight? Does that mean candlelight? You know, what is in this case, your operational definition of light? Or what do you mean by hot? Is there like a temperature cutoff for that where we're going to say above this it's hot? Putting students in that position of having to identify which words need that and then to provide the definition. Letting them do this individually, but also doing it in groups. So sitting down together in groups and talking about kind of different ways that things could be misinterpreted, different meanings of words as they come to their agreement about what the operational definition will be for them. It really helps them to be able to include ways others might see the word in that process. And then the next one, discussing differences that we have in operational definitions. And you know, part of that is being really clear about where there's a compromise, where there's an actual definition we need to turn to. But another part of that is just being clear that because there will be these differences, you know, we always need to state our operational definition, state what we mean by things. The next one is experimenting. Experiments in many ways are the meat of doing science. Alone, they don't get us very far. We need to do a lot of preparation before we experiment, or the experiment will be meaningless, and we need to do some follow through afterwards or we won't learn anything from it. Students should have the opportunity to do a few things. One, they should be able to experience a well-designed experiment. Pre-designed or canned experiments are good for that. Students should really be able to experience that feeling of success, that feeling of what goes right and what it feels like when it goes right. They should also have some experiences where they have limited choices about what to do. Maybe this is a modified version of a pre-designed lab that kind of opens up some choices, or an open-ended lab that you put some limitations on, where students are able to really have some ownership of those choices, but not allowed to kind of go off a cliff and do something that's never gonna work out for them. And other things, students should be able to start with variable identification and move all the way through the process of designing the lab. You know, when we talked about identifying what variables need to be held controlled, identifying what the independent and dependent variables are, and then talking about how you're going to control a variable. As you do that, you're really beginning to design an experiment. And so allowing students to take that and move it to that next step of saying, and this is how I'm going to use my independent variable to affect my dependent variable. This is how I'm going to do my experiment. And, you know, upper elementary and older children should be able to do these once you've shown them how. You know, once you've gone through that process once, they can do it in groups, and they should eventually be able to do it independently. With young children, you can do this as a large group and give them that practice of doing this together. And then the last one, students should have the opportunity to do whole class observations and hands-on experiments. The purpose of a whole class observation is that you can model good experimentation practices, safety, good reasoning, good use of tools, whereas hands-on opportunities, they're able to practice their own experimentation skills, which is really important for them to develop that independence as a scientist. Constructing models, this is one that I have had you kind of watch the video, or I've asked you to watch Paul Anderson's video explaining about constructing models. So it's really important to allow students to practice with all the different types of models, because using models is a huge part of what scientists do. They save us time, they save us money. They're used to show us things that are way too large or way too small, or with patterns that we want to see that happen over a very long or very short period of time, or just with things that change quickly when we want to get a static look at it. So they provide us with all these different opportunities to really work through things. So the types of models that Paul talks about in his video that I'd like you to kind of think about providing experiences with are mental models, diagrams, replicas, analogies, mathematical models, and simulations. And I'm not going to go over those types because he does a great job. And also, I think that it's good to make sure that you're allowing them an opportunity to create their own model and then interpret and use the models of others. And this is one of the things that I've asked you to really think about, how this changes across grade levels. The types of models that students are ready for varies drastically. this week you have 6 guiding questions. I want you to not try to write a book for each of them, but for each one to at least provide a response that kind of answers the question about what you saw as you went through the different exemplars and what your thoughts are about how these processes fit together. Have a great week.